I'd like to talk to you about impulse and momentum. So I'm going to go through and do the notes kind of two different ways real quick. It's not going to take long. I'm going to do a little bit of work just like I would do for physics, for first year intro physics students who don't have calculus. If we don't have calculus, then there's lots of things that we can still do, and there's some things that we can't do. But we can always do kind of like approximation versions of what we can do with calculus. The thing that you can't do if you don't have calculus is you can't deal with like complicated change. You can basically deal with just with things that are linear, and if you think about integrals and area and stuff like that. So here's the regular non-calculus version of introducing impulse and momentum. So here's Newton's second law. You know what it is, right? 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 Sum of all forces is equal to mass times acceleration. Okay, what's acceleration? Well, if acceleration is if whatever that force, whatever the imbalance in those forces, if it's constant, then A is constant. And if A is constant, then A is just equal to, then velocity time would be a straight line, so A would be equal to delta V over delta T. Right? So let's just say that the sum of all forces, let's just say there's one force. Let's just isolate the unbalanced force. Call that the imbalance. I don't want to keep writing that sigma there. I'm going to clean this up so it looks like what I want it to look like. Mass times delta V over delta T, and then algebra, could write that like F, multiply that up over here. So that is, nothing like groundbreaking, earth-shattering. Earth-shattering? Is that a thing? Nothing super crazy happened here. I mean, we really certainly we didn't introduce any concepts that we don't already know. But this is an interesting expression. Like, this manipulation has resulted in something that is like kind of a different way of thinking about forces and motion and stuff like that. What this tells us, if we take a step back and think about what this is saying that a force applied over a period of time, so some force times the amount of time that force was exerted for, that is equal to mass times change in velocity. And we're going to define these things. We're going to call this force applied over some period of time. I'm just saying average here. I know I said it was constant, so this, in general, if it's not constant, then we could just use the average force. That we're going to define as impulse. And I would definitely appeal to the fact that that is a dang good name for that, right? If you think about like a force like punching at something for like a brief period of time, it's appropriate, it's correct physics language to say that that is an impulsive force, that force delivers an impulse. That force times the amount of time it's doing its thing. And then what about this side here, mass times velocity? We're going to define this, I'm going to call that momentum. You might be thinking to yourself, okay, why would we do that? Because we already have a physical quantity, kinetic energy, that depends on mass and velocity. We already have kinetic energy is equal to 1/2 mv squared. Why would you do this? And the answer is because it comes up in the context of this. So why did we do 1/2 mv squared? Because that came up in the context of work and doing stuff like that. So we name these physical quantities. You don't go off like, on a spiritual quest and then come back with some idea. Oh, I have a new idea for a physical quantity. Let's take this quantity and raise it to the 7th power and then divide by time and do... No, that's not how it happens. All of these physical quantities come up and get named because of the fact that they come up in this kind of just pushing things around and paying attention to what's happening. So, what if that force is not constant? So then, let's say we had a force versus time graph, and we have some force that is not constant. What about that? And let's say it stops acting like here. Well, we're doing multiplication here. Like if we want force times time, so you could think about like if it was constant for like little tiny bits of time, you could make like a Riemann sum here, right? You could say, well, here it's like pretty much just this, and like very soon you should realize that, oh, the thing that we're interested in here, if we want force times time, we're interested in the integral. We're interested in this area. If force is constant, then your force versus time graph looks like this, and of course you could interpret force times time as force times the area of that rectangle. So, Riemann sum, then limit, blah, 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 area, so we're talking about an integral here. I'm just going to shade that in because I feel like it. Don't go outside the lines. All right, that kind of went outside right there just a little bit. So we are going to define impulse, and don't ask me why. The symbol we use for impulse is a capital J. If you're wondering why not capital I is reserved for something else that we're going to study pretty soon. I think in chapter 10, actually, in the next chapter. So I don't know, Gympulse, if you like. So you're not going to see that a whole lot. Most of the time, the impulse. I'll show you the equation that you're going to see the most in a second, or that version of it. So we're going to go from it's time 1 to time 2, some time interval of the area under a force curve, but it has to be force as a function of time, not force as a... If you're looking at this and thinking to yourself, wait, I thought we did the integral of force. We did, but it was the area under a force versus position graph. This is the area under force with respect to time. And all of a sudden now, we sure do have a context, I think, where we can appreciate that little d whatever, right? And the way our calculator is always asking us, like, what variable do you care about? And you're like, oh my God, it's x. Like, how many times do I have to tell you x? Well, it's not always x. For your calculator, of course, probably just going to be x. But you can use different letters there too. Here, this is super important because this is the integral of force with respect to time. And to leave that off would be a grave mistake, because how would we know whether you're talking about this integral, which is equal to impulse, or the integral of force with respect to position, which is equal to work? So important for sure. That is equal to mass times change in velocity, which is momentum. So momentum, we're going to use a lowercase p. Sorry, lowercase m, that's mass, was taken. So just rummaged around in the alphabet nearby to there. Didn't like O, because that looks like a 0, so there you go. So delta mass times velocity. And actually, we should really write that. The mass isn't changing, so mass times change in velocity. That would be a better way to write that. And that's change. Oh, I know what I was going to write there. I was actually going to write the word delta momentum. So there's a nice complete definition of all these things. Now, if you want a justification, you might just buy into this because you're like, yeah, Riemann sum, I get why it would do the same thing. But I just want to show you some cool calculus. Here's just a little proof. Once we have these things defined, what's the integral time 1 to time 2 f dt is equal to, well, force is mass times acceleration. Just assuming that that is like the force, the one and only, or the imbalance in force, dt. Okay, so acceleration here, and here this variable is time. So I can't just say like the antiderivative mass is constant. I can bring that to the outside. I will on my next step here. I can't just say the antiderivative of a is a squared over 2, because the a is definitely not constant, right? But it's not the right variable, right? This is the integral with respect to t. So what do? Well, I know that acceleration is dv dt, right? And then something kind of magical happens. The dt's cancel out. And we see another like huge advantage to the way we've chosen to do this notation here. The dt's cancel out, and I just end up with this. So what is that? Well, that's like what's the antiderivative of like 1 with respect to v? Well, the antiderivative of 1 is just v, right? Just like the antiderivative, if x is the variable that you care about, antiderivative of 1 is x. So the antiderivative here is v, t1 to t2. And what happens when you like plug in this? Well, that gives you m. When you plug time 2 in here to this v, then you just get whatever the velocity is at time 2 minus mv1, and of course that's just mass times change in velocity. So it doesn't matter whether your force is constant, or you know the average force, or you got this situation. It still works. So impulse equals change in momentum. If you want to say it in words, that's what you're going to say. Impulse equals change in momentum. If you're going to write it down in symbols, you're going to write it down as impulse equals change in momentum. That's it.